got a chance to do maybe some barbecuing and a little relaxing.
Yes, sir. Very relaxed doing the lab work.
Yeah. Well, I know that didn't take all weekend.
I was just tearing down brakes.
Oh, there you go. Nice. So doing the rear brakes on it, huh?
Yeah, it's amazing what you find.
Yeah. Axle seals leaking?
I'm not going that far. I don't want to. Some things you don't want to know the answers to.
Well,
So
if
no,
they're
it's
leaking,
just
you'll see gear oil everywhere. So if they're dry, they're not leaking.
hard to tell difference to me whether it was gear oil or brake fluid. Yeah.
Smell.
Hmm.
It's all about smell.
All
Plus,
dirty.
brake fluid will clean off with water. Gear oil will not.
That's a good point. That stuff's definitely not coming off with water.
Sounds like you need some new axle seals. Now you have a Ford 9-inch in the back of that, I'm assuming.
Yeah.
Okay, so that's real simple. You got 4 bolts that hold the backing plate and the axle in. You take that off, you take it to a machine shop or rigger shop, they'll press new bearings and seals on for you. And then you put it back in with 4 bolts. So it's well within what you can do.
Yeah. Hey, should there be any play? There's a little bit of play in the axle.
Yeah, there's a little bit of play back and forth. That's the backlash in the ring and pinion. That's normal.
Okay.
But how that goes together is there is a seal, a bearing, and a collar, and the collar holds everything in place. So the 4 bolts have that flange. So when you take those 4 bolts or nuts off, that whole thing will slide out, and you just take that down. And the left and right are normally different lengths, but I'll use like a center punch and put 2 marks on the right side so I know which one's right when I get them back. And you go down and they'll put in new bearings and new seals and press that apart and back together, then you're good to go.
Probably worth doing since I got it all apart anyway.
It's worth doing, and if you have stuff there that's not clean off with water, that's gear oil, and the gear oil will just damage the new brake lining. So
yeah,
whatever, you don't need to do both sides. You can do just the one side or do both. It's up to you. Whatever side's leaking, but those are a press fit bearing and seal setup on those. And then there's a lot. Some of those had an inner seal that also went in there, so you had an inner seal and then an outer seal. But if I remember correctly, the 9-inch didn't do that. The 9-inch only had the outer. And so, like I say, take it in, and any auto parts store with a machine shop or any good, shop with a press will be able to do that for you and press those. And like at a auto parts store machine shop, I'd expect about $50 a side, $50-$60 a side labor, plus the bearings and stuff. So you're talking probably $100 and change a side, something like that.
Cool.
And again, that's a lot cheaper than paying someone to take it apart and do all the press and do everything else, where you're talking a pretty expensive job. So that way you could save some money, but not go too deep.
Yeah. The fun thing I noticed was how they had at least on the driver's side, the shoes were reversed.
Oh, they had the primary shoe in the back?
Yeah. Yeah.
See that a lot.
And that was someone I paid to do, I don't know, probably 18 years ago. I had somebody do that,
Like I said, happens a lot.
Yeah.
Either people aren't paying attention or they don't know, one of the two. So today we are going to finish up on lubrication.
If Groman will stop talking. Okay.
So no, today we are going to finish up on lubrication because we need to get into cooling. I want to get cooling done this week. So that way we can get into ignition next week, because time is flying on us. And several of you turned in the oil lab, and you did see that I think everyone drives in severe conditions at some time if you think about your driving here in Southern California. So that's something that really isn't explained to us when we buy a car or when we look up service. So even the best oil is useless if it cannot reach the engine's moving parts. The job of lubrication system is to get oil moving, get oil to the moving parts of the engine. So on automotive engines today, we use a combination system of pressure lubrication and splash lubrication. So pressure lubrication is where I have an oil pump. I'm going to pick the oil up and I'm going to force the oil into certain places. And we do that for our friction bearings, is the primary place we force oil pressure into. And that's what allows us to use an oil filter. So I couldn't have an oil filter unless I had a pressure lubrication system. And then also have components of the system that are splash lubricated. So the timing chain, a lot of my valve train, rocker arms, things like that have oil just splashed on them, and that's enough lubrication for those things. So I don't have to pressure feed everything. There are systems out there like on air compressors and lawnmowers that are a splash that don't have a pressure lubrication system and are just splash lubricated and rely on the crankshaft actually going through the oil and throwing the oil up. And a lot of times I have a little scooper and it throws the oil throughout the engine. And that's why lawnmowers don't last very long. So lawnmower engines just don't, hold up very long. And you're thinking to myself, wait a minute, I've had a lawnmower for 10 years or 15 years. Well, let's think about how many hours runtime that is. Because we know we don't mow the lawn every week. We don't need to mow it year round. And how long does it take you to mow the lawn? Is it a half hour? Maybe you have a big lawn, an hour. That would be huge. So odds are that mower fires up and runs for 20 to 30 minutes, maybe 30 times a year. So you call it, if it's 30 minutes, that's 15 hours a year. 10 years is 150 hours. 20 years is 300 hours. So if my average speed going down the highway was 60 miles an hour, I took 60 times 300, that'd be 18,000 miles. And that's if I was doing 60 the whole time. So in reality, we know our average speed on the car isn't that. So you could see where lawnmowers, when I say they don't last long, they really don't, because they're a splash lubricated system. So lawnmowers, air compressors tend to be strictly splash lubricated, although you can buy lawnmowers that are pressure lubricated. Commercial ones are. Like my lawnmower has a spin-on oil filter and a pressure lubricated system. My air compressor does not, but they do, like I said, just like anything, how often is it going to run, what kind of service life, and depending on the service life and how much it's going to run, you need to start upgrading the lubrication system, not just the lubricants you put in here. So in this picture here, we can see the vehicle using a pressure or force-fed lubrication system where oil is pulled from the pan through a strainer. It's pulled in by the pump. After the pump is going to go to the oil filter, then it goes into my main oil galleys where it's going to be sent to the crankshaft. The crankshaft has hollow ports inside that go up to the connecting rod bearings. And so we're pressure lubricating all that. And then we're going to send oil pressure up to the camshaft and pressure lubricate the camshaft. So the camshaft, lifters, variable valve timing, those are the things that get the oil the last. On a friction bearing, oil is used between what two components in order to reduce friction?
Any approval?
I'm sorry, what?
Number 4.
Not number 4.
3.
Number 3, between the bearing and the spinning shaft. Number 3. Because remember, the housing doesn't move. I don't need to lubricate between the housing and the bearing. The housing's holding the bearing. So the part that's rotating is the shaft. And that's where we need to put the oils, between the rotating shaft, whether it's a crankshaft or a camshaft, and the bearing. So we have 2 different types of oiling systems we use on automobiles. We use what's called a wet sump system or a dry sump system. So a wet sump system has oil in the oil pan, and we have a strainer in the oil pan where we use difference in pressure. We create a slight vacuum, pull oil up into the pump, and then circulate it through the filter and into the rest of the engine. So most of the cars on the road, 99.5% of the cars on the road, or 99.8% of the cars on the road use this system. There are a few cars that use what's called a dry sump system. So a Porsche 911 was one of those. And the advantage of this is that the crankshaft cannot hit the oil in the pan. I can make the pan shorter, so this is great for clearance, as well as now I'm using a low pressure pump to pull stuff out, over to an oil hold tank and then a high pressure pump to put oil back in the engine. So this is a real advantage for racing, because if I'm cornering real hard, going uphill or downhill real hard, I have constant oil supplied to the engine. So to put in perspective, a Porsche 911 six-cylinder engine would hold 9 to 11 quarts of oil. That's a lot of oil for a small six-cylinder engine. And one reason why I use so much oil is because it had that oil tank. Another reason is it was air cooled, so it used the oil entirely for cooling on these older ones. But this is a dry sump system, so you'll hear wet sump and dry sump. The oil pans can be broken into a couple parts. So this right here, what we're actually looking at is a sub pan, because you see how shallow it is. I'm not holding 4 quarts of oil in that. So this will have an aluminum main oil pan and then a tin or aluminum sub oil pan, very common on cars today. And here's our drain plug that we always want to replace the seal on the drain plug anytime we pull it out. This is a windage tray. Windage trays are used to keep oil away from the crankshaft as it's spinning. We saw those a lot on older vehicles, especially trucks going back to the 70s. A lot of cars today have baffles in the oil pan. And one of the purposes of the baffles in the oil pan, we'll see them vertical as well as horizontal, is to control the movement of the oil in the pan as we accelerate, decelerate, side to side, cornering, and to make sure we keep the oil down, away from the crankshaft, but also so the sump can pick it up. And here's what I was talking about by splash lubrication. So this is from something like a compressor. Here we can see I have a camshaft and a crankshaft. I'm using gears to connect the two. And I have a little slinger that's going to come through and grab oil and just toss oil around inside here. So we're just splashing oil in here. So you can see where using this system really limits how much power I can put into this combustion chamber and push down on the piston, because the more power I make here, the more force is applied on this surface here, the greater the effects of friction. So I can use this on low power applications like an air compressor or like a lawnmower. And certainly old cars, if I go in the Wayback Machine, go back 100 years, you'll find that engines were splash lubricated. But engines didn't last very long either before they had to be taken apart and rebuilt. So that's why we use pressure oiling system on all the parts that require oil to be forced into them, and then rely on splash lubrication for the areas that we can just allow oil to drain over to keep it lubricated. So what type of oiling system is used on modern automobiles? Combination of pressure and splash lubrication. Absolutely. So components of the pressure splash system, the combination pressure splash system best meets the needs of modern engines, and therefore almost universal use. I can't think of anyone who doesn't do it. Oil is constantly drawn from the bottom of the engine, pressurized and distributed to engine parts. The oil then drips to the bottom of the oil pan sump and begins the circuit all over again. So the first thing we have is what's called a pickup tube. Now the pickup tube will have a coarse screen on it. So this coarse screen will pick up large contaminants. So it's really, although it's made out of a heavier metal, the screen's about the same size as the screen you see on your window. So anything that can get through your window screen is going to be pulled up into the oil pump. So this is really designed to keep big particles out that would damage the pump, because we don't want to damage the pump internally. The downside is that if I have foreign material in the oil pan, such as silicone, where someone cleaned valve cover, gas cleaning service, and scraped it, and it just ended up in the engine and they didn't get it and it ends up at the bottom, or if we have a lot of buildup from burnt oil or bad oil where we get a lot of carbon formed in the oil, carbon chunks, both of those can plug this screen up. And if this screen plugs up, then we're going to starve the engine for oil and very quickly damage the engine. So that's why we really don't want things to end up in the oil pan. Even though they can't get sucked up into the oil pump if they're big, they can block this screen. And when the screen gets blocked off, it's kind of like drinking a milkshake through a straw and you hit a piece of ice cream. You're no longer getting any milkshake, right? Because this ice cream is blocking the bottom of the straw. Same thing happens here. So as we're pulling oil in, if this gets blocked, then we lose that. So a common symptom of a plugged screen is that I may have the oil light will be off at idle, but when I rev the engine up or if I drive the vehicle at speed, the oil light comes on. So if the oil is full when that's happening, one of the common causes of that is a plugged screen. Conversely, if I have a bad oil pump, in other words, my pump is not producing enough pressure because the pump is worn, my light will flicker or come on at idle and go off when I rev the engine up. So both are low oil pressure. That's why the low oil pressure light's coming on or the gauge is reading low, but two different causes. And so based on when the symptoms are happening, I can quickly determine what am I looking for? Am I looking for a bad oil pump or am I looking for a plug screen? So we use a couple of different kinds of oil pumps on the engine that the book goes into. They all do the same thing. They all pull oil from the oil pan and put it into the bearing journals and the galleys of the engine. So they force oil under pressure through the lubrication system to deliver oil to the parts that require lubrication. They're normally driven by the camshaft or crankshaft. So depending on the pump design, depending on the vintage of the vehicle, they can be driven by the camshaft, the crankshaft, and some today have their own little timing chain and mount as an oil pump cassette underneath the crankshaft, but it's still driven by the crankshaft. It's just connected by chain, not directly. Rotor type oil pump, the inner rotor drives the outer one, and the oil is forced in the pump outlet. Higher atmospheric pressure outside forces oil into the pump, and it fills the spaces between the rotor lobes. So one of the things the book does that I think is really confusing is they keep mentioning, and they do this with the fuel system too. They say, well, it's higher atmospheric pressure that is allowing the oil to be moved. Well, it's really the lack of atmospheric pressure, vacuum, that's causing it to move. So they're both saying the same thing, but I don't think if I'm drinking my milkshake with a straw, I would say it's the fact that I'm creating a vacuum by sucking the milkshake through the straw that is causing the milkshake to come up the straw, not the atmospheric pressure pushing the milkshake up the straw. Right? I mean, both are true because the atmospheric pressure pushes it up because I've created lower pressure in the straw. But it's not how we normally think of things. And I find this to be confusing how the book describes it. And they do this for a couple systems where they talk about the atmospheric pressure pushing it. Well, the one is why the atmospheric pressure is able to push it is because we've created low pressure through a vacuum at the other end. So I would argue it's the vacuum pulling it, not the low pressure pushing it. Because if I put a small hole in my straw, do I still get milkshake or do I get less milkshake and a bunch of air or maybe just air? Right? I'm still sucking, but I'm not creating that vacuum and the atmospheric pressure hasn't changed. So I really, I think from a diagnostic standpoint, I think thinking of it as vacuum pulling it makes sense. Because then if I have a bad gasket between that oil pump and the pickup tube or a bad seal there, right? My pump is still drawing. I still have atmospheric pressure, but now I'm going to pull air in instead of liquid because the air weighs less. So that's what's going to be pulled into the vacuum. And I think that really leads us to when we get into diagnosis, why is fuel not moving? Why is oil not moving? Why is something not moving? When are we putting it under vacuum? And if we are putting it under vacuum, do I have a sealed system back to the heavy thing I'm trying to move with vacuum? I don't really think of, like in the gas tank, I don't think of it being atmospheric pressure pushing fuel into my engine. I think of the vacuum from the pump and then the pressure generated by the pump pushing fuel, putting fuel up to my engine. I mean, it's all about pressure differential, but the book just describes it this way. And I think it's really confusing and it doesn't lend well to understanding or diagnostics, I don't think. So a couple other type of pumps. I can have a geared oil pump. So this first pump here, very common pump today, the rotor type. This geared pump, we still use these today, and these were used a lot back in the older engines. And then the crescent pump. The crescent pump we see on a lot of import vehicles. Toyota comes to mind, but a lot of import vehicles use a crescent pump. And the crescent pumps are mounted on the crankshaft. So the center of the crescent pump is actually, the center gear is actually mounted onto the crankshaft. And where these other two ones can be driven by chain or driven by a shaft, but they're not going to be mounted directly on the crankshaft. But the crescent pumps are always mounted right on the front of the crankshaft. And that's where they put them. And this is important because if I have an oil pump problem and I need to work on the oil pump, where is it? Do I need to take the oil pan off to get to it because it's underneath? Or do I need to take the front of the engine apart because it's a crescent style and is mounted or part of the front cover? And that's where research is really important. Oil pumps will last the life of the engine. They are normally replaced anytime the engine is rebuilt. Oil pumps, sometimes you only get one choice of oil pump. Here's the oil pump for this engine. On many domestic products, especially if I'm talking, V8 engines or older engines, where we're using a geared oil pump, I can buy a standard oil pump, or for a few dollars more, I can get a high pressure, high volume oil pump. And when we rebuild engines, we always put in the high pressure, high volume oil pump. It's literally $5 to $15 more. I mean, it's very little more. And what it does is it buys you a little bit more space if tolerances are out. Plus, the customer's never going to have an oil supply issue on that engine. And it's going to get better cooling. And I see I have a question here. It flickers on startup only and under no other conditions in the issue. Well, I'd be a little concerned with that because it shouldn't flicker on startup. So a couple of things come to mind. We could be having a little bit of a bleed back issue, so it's taking a minute for it to pressurize the whole oiling system. So that would just be some signs of some wear, which is fairly normal. And other questions, are you running the manufacturer recommended oil in it? So those are the two things. So if you're running the manufacturer recommended oil, and if it flickers for 3 seconds on startup, I really wouldn't worry about it. If it's sitting there flickering for 30 seconds or a minute, I'd be concerned. And it may be something as simple as a bad sending unit. But yeah, just a quick moment. As long as you're running the right oil, I wouldn't really worry about it. We do see that sometimes when oil is old, oil filters old, things like that. But it's not something I would go in and start taking stuff apart for.
A quick question on the high volume pump.
Yeah.
So again, this comes from these forums that you love. A lot of comments that I've read about the high volume pumps pumping. A complaint about it, you get too much oil just hanging up in the top of the valve covers. Like it's so much volume, it's throwing it up there, and so you're losing it down low. And I never buy into it, but I want to ask you about that. Is that
no,
a thing?
Absolutely not. You have huge holes for oil to drain back, and you have plenty of oil in the crankcase. Okay. So you figure you got 5 quarts of oil in the crankcase. You're going to pump oil until you're down to about half a quart. So is it really a difference? I mean, say they're right. Say I put more oil on the top of the engine. Is it really a difference whether there's a quarter quart or a half quart of oil on the top of that engine?
No,
none. So again, I think
there's still some in the pan, still.
Yeah, you got plenty in the pan, you're under pressure. And if anything, now you're going to better splash lubricate. And everything is designed so where the valves sit and everything else, it pitches away from it and goes in the drain back hole. So you can't submerge anything. And the amount of oil that's going to be static up there that doesn't drain doesn't change how much oil I put on there, because we're going to fill those little cavities, whether I put it up there a little at a time or a lot at a time. The difference is how fast is it draining back to the engine. So, if I put it up there, it's coming down. It's like if I have a water hose and I put it up in the air, and all the water comes back down, right? I'm spraying it up. It's all going to come back down. Now let's get a bigger hose and do the same thing and say, well, this bigger hose is bad because it puts more water in the air. Yeah, but it's all coming back down and we're recirculating. I mean, and since oil cools the engine, the more oil you can move, the better. So yeah, I'd say that's a garbage argument. And I mean, it's interesting the stuff that people kind of pick out or, experts on, quote unquote, or it's like, really? Yeah, no, and I could tell you in industry, that's all we put in when we do that. I mean, again, it's cheap insurance. And the funny thing is, a lot of people probably have a high pressure, high volume oil pump in their engine and they don't know it. Because just like your engine, it was rebuilt. I'd be willing to bet the builder put the high pressure, high volume oil pump in.
Yeah, the guys that installed it did. I know they put a high volume pump in.
Right, exactly. And you would, and they're doing it because they want the insurance. They want the fact it's going to cool better, not have issues. And again, I mean, last time I bought one for like my pickup truck, I think the standard one was $55. The high pressure, high volume was 60. I mean, why wouldn't you?
Is it both? It's a high pressure and volume, or is it just volume?
Yeah.
Or is
Pressure is controlled by the system, and it goes against a pressure relief valve, which we'll see.
Right.
But if I have low volume, I'm never going to overcome that pressure relief valve. So with high pressure, high volume, now I can change the pressure relief valve if I want and make more. Some pressure relief valves are built into the pump, so they will actually kick the pressure up 10 PSI or whatever. So it depends on where the pressure relief valve is. Is it in the pump, in which case high pressure, high volume, one and done. The other is because you're able to make more volume, you can make more pressure because you're filling everything up before you do it. So you're going to hit that pressure relief more often. So they generally call them high pressure, high volume pumps. Whether or not you're really moving the pressure or not, it depends on where the pressure relief valve is. If it's in the pump, then yeah, it's going to be slightly higher pressure. Usually it's like 10 PSI higher. I mean, you're not going from 60 PSI to 100, although you could if you re-engineered it. Because you don't want to go too high because then you start pushing filters off or popping filters apart or creating other issues. So and the manufacturers of these things know that. So they move it up that safe amount. So you're picking up a little bit more. So yeah, I got 10 more PSI. And I'm circulating the more oil more often because I'm higher volume. The more I circulate it, the more I move heat. The more I move heat, the longer my engine lasts. Because, we know that if oil's staying there, it's getting hot. And so we want to change it as often as we can. Again, and a little bit more oil pressure. Think about it. We're riding that non-friction bearing against the journal on oil. So more pressure is going to give me more, more shock absorption and more protection. So now I do have a question here about checking the oil. How long do you need to wait after turning off the engine before you can trust the dipstick level? Great question. Rule of thumb is 30 seconds to a minute. You don't need to wait real long. Some manufacturers do have longer periods. Some manufacturers like Jaguar say you have to check it within 2 minutes or it's not accurate. So manufacturers, some of them say, so normally we shut the car off in about 30 seconds, we're pulling it and checking it. And that's a good thing. Obviously, if I leave it off for an hour and check it, I'm going to be over full probably because all that oil is drained down that would normally be suspended in the engine. If I check it too soon, I'm going to read low. So some manufacturers have a max time. Some manufacturers have a min time. In the shop, it's normally about 30 seconds. We're checking it. We just pretty much do everything that way. And that seems to hit the sweet spot. How long were you waiting? Oh, cold. Okay. And see, that's going to show it a little higher because everything's drained. Your manual said 15 minutes on your Explorer, huh, Tim?
Yeah, just found that from going through the lab this weekend. And I'm like, oh, 15 minutes after shutting it down, huh? That's what seemed like a long time.
That is a long time. So they want all that oil to drain down. So they're really looking for putting minimum amount of oil in the car. right? Because the longer it drains down, the less oil you're gonna need. So that's interesting. I can tell you in a shop, no one waits 15 minutes. You think about it, you go through a drive-through quick loop, you're done in 15 minutes. So no, that like, and that's what I was saying. Different manuals, I've seen a lot of different numbers. Some are you need to check it within 30 seconds. I mean, so it's all over the place. I can tell you, like in a shop, we shut them off and then we check it. Yeah, see, Cynthia, accurate 30 seconds. And that's about the time it takes for me to shut the car off, walk around to the front, grab a shop towel, check, pull the dipstick, wipe it, drop it back in, check the level. It's about 30 seconds. And that's what every shop does. Unless there's something that's caused a comeback issue where, gee, we've put a quart in too much or left it a quart shy because we checked this year, make a model the way we did everything else. And that's when you get into, oh, this is special. And there was a couple Jaguar motors like that.
And I just found that out while working on the lab work.
Yeah. And that's why I have you guys do the lab work, so we can learn this stuff. Because every car is kind of unique. Neighbor's Audi doesn't even have a dipstick. Yep. So you check it through the dash. Or trust that it tells you when you're out of oil.
That took a long time for me to figure out. I'm looking everywhere underneath the, where's the dipstick?
Yeah, a lot of cars don't have a dipstick, just like a lot of cars don't have automatic transmission dipsticks, because they figured out that customers either put the wrong lubricant in or don't do it right. So they really want it sealed until it comes back to a service facility, because customers do bad things. So which oil pump design is mounted on the front of the crankshaft?
Number 4.
Number 4, the crescent.
Crescent.
Most engine oil pumps are driven in one of 2 ways, a drive rod from the camshaft or directly by the engine crankshaft. Like I said, we are seeing a gain where they have their own timing chain. Mercedes did this, Volkswagen did this, and so on. Many newer engines use a pump installed in the front cover and driven by the crankshaft. Honda, Toyota, a lot of other ones. So oil pressure relief, we were talking about this a little bit. So the oil pressure relief valve is a spring-loaded valve. So when I have enough pressure to overcome the spring pressure, we start bleeding off that extra oil back to the oil pan. So oil pressure is affected by the size of the leaks in the system. So if I have a very tight tolerance, I've got a lot of resistance. As the engine wears and the tolerance gets bigger, it takes more oil to fill that and keep pressure. And that's why we see pressure drop as engine wear increases. Again, talking about the difference between a standard pressure pump and a high pressure pump with a high pressure pump, right? You're higher up the mountain, so it's going to take longer to come down to where you have a problem. So that's a big reason why industry does that. So here we have, low leakage versus high leakage. We can see the pressure change, high pressure, low pressure. So oil pressure is affected by changes in the volume of oil flowing also. So the more oil I flow, right here, high pump speed, for example, or high volume pump, we're going to increase pressure. So we're following it so far. I haven't even brought the pressure relief valve in yet. We're just filling up that area because the pressure relief valve doesn't come into effect until I hit that maximum system pressure. Now, is that maximum system pressure 80 PSI, 90 PSI, 60 PSI, whatever it's set at? So if I have a low volume pump, I'm never going to hit the maximum oil pressure in the system. Again, provided that pressure relief valve, whether it's built in the pump or not built in the pump, that's why as we lose volume or I lose restriction, just like my thumb over the end of the hose, right? So I can have a lot of pressure come out the end of the hose, even with the faucet not turned on very far. If I put my thumb down really far and just let a little bit of water out, I can get a pretty good spray distance out of it. But if I take my thumb off, then there's like barely anything coming out. If I open up the hose more, now I don't need to put my thumb over the end as much to shoot the water just as far because I'm flowing a lot more water. And so on these systems, think about I need a certain amount of pressure to let that out if I'm not making enough pressure, we're never going to open up that relief valve. So here, if we look at the relief valve here, as my pressure gets up to a certain point, then we overcome the spring and we allow the oil pressure to be released back. And so these relief valves, a lot of them are made into part of the pump. Some of them are on oil filter housings that. So we do see some other locations for this. Front timing covers. And this is a spring and it's shimmed. So, I mean, I've worked with people that they go through and they actually will add shims in here to increase the tension on the spring. So it's harder. So it increases the amount of oil pressure that the system can do. And that's how I know that you get over 100 PSI, you start blowing oil filters apart. Because I've seen oil filters blow apart from people playing with this, right? You know, if a little is good, a lot's got to be better. Well, there's a point that it's not better. So having the higher pressure volume pump is great, but you still want to have that pressure relief valve set at a reasonable level. And so if I'm buying a pump with a pressure relief valve built in, I'm going with the engineers that sold this pump to me. Have already done the research and know what the filter and everything else is going to handle. Because you think about the liability. If I put their pump on and it blows my filter off and I blow up my engine, they're getting sued. So they're not going to do anything crazy with it. They're going to go far enough that they've tested, I'm not going to have a problem with. So I'm kind of a big believer and I don't need to reinvent the wheel. So does this help a little bit with the pressure and volume discussion we had, Tim?
Sure.
Okay. That was a quick sure. Are you sure?
I couldn't get my mouse to, whatever, it's fine.
Okay. So oil filters, two different types of oil filters we use. One is a full flow filter and the other one is a bypass filter. They use a pleated paper for filtering the medium. So one of the issues we see, and all filters have a bypass valve in them. One of the issues we see is that people go, I went all this time and my stuff's fine. Well, how do you know your filter didn't plug up 5,000 miles ago? And now you've been around the last 5,000 miles without a filter because you're just bypassing it. So filters are not all the same. They vary by the amount of capacity. How are they flowing through the filter? Most filters go down to about 20 micron is what they filter down to. And you can, like on the Napa site, you can see the specs on what your filter goes to. And the other big thing is surface area. So we can see here we have a pleated filter. And so this paper zigs and zags and all that surface area for the oil to go through. So if I have more pleats, that's more surface area, right? I can also circularly wind the filter. Deeper filtration, I'm using less surface area, but more filtration. The other big distinction between filters is I'm using a spin-on filter or a cartridge filter. So spin-on filters became very, very popular in the 1960s and have kept popularity. We still have a lot of manufacturers that use spin-on filters. Cartridge filters is what we used prior to that in the 1950s. Some European vehicles continue to use cartridge filters up into the 90s, up into the 80s, excuse me. And then we saw in the 90s that all of a sudden all the Europeans went back to a cartridge filter. And that is because in Europe, they're really concerned about all this metal going into the waste system. So they only want the paper filters. And by paper, I'm using the term generically. They are made out of other things besides, like, for example, Mercedes uses a fleece filter on some of their cars because that's the only way they get the service interval because the paper will break down before the oil will. So they use a fleece filter. So I'm using the term paper generically. But the European market said no more spin-on filters in Europe. So that's why European cars got this. Even my Toyota uses a cartridge style filter. So that hasn't really taken full hold here yet, but a lot of manufacturers that either are based in Europe or sell a lot in Europe have gone to that cartridge style filter because of the European regulations. In this country, we do recycle oil filters when we send them in. Most common thing we recycle the spin-in oil filters into is rebar. It's the most common thing, at least in California. The paper, on the other hand, has to be disposed of and cleaned up. There's oil in there, so you're going to get oil out of it. Then you got paper, so there's a whole process. So filter operation, here is a regular spin-on filter. And we can see the oil comes in through the outside, through the pleated paper, and out the inside and into my oiling system. That's why when you're taking off the plastic that goes around the filter, you never want to put your finger in the middle to pop the plastic in. Because occasionally a piece of plastic will end up in here, gets forced into the oiling system, and I've seen it destroy tops of engines because it plugs up the oil port. I got some cool pictures of a camshaft in 2 pieces on a Honda with 5,000 miles because the service tech at the dealer did that. So, and here is a deep depth type filtration. So you can see here, instead of the pleating, I've got a lot more media we're going through, and this media has an infinite number of paths through it. And then it comes out here. Both of these have a relief valve in them. The relief valve is there because my pump is making pressure. If I have too much restriction in the filter, we're going to push through this relief valve and we are no longer going to be filtering our oil. Some filters also have a valve. This might go back to the question because I didn't ask what kind of car was the oil light was flickering. Some filters have a drain back valve in them. Honda is one. So in some cheap filters don't have that drain back valve. So it'll drain the oil out of the galleys, off the camshaft. So the oil light will flicker or it'll stay on for that 3 seconds or 5 seconds when you start the car. We're using a good quality filter that's made to the OE specs that has the drain back valve in it. We'll keep that from happening. Now, not all cars use a drain back valve. And I didn't ask what kind of car you were getting the oil flickering light on. I really didn't think about it till we got to here. But that is something also. And I've seen that on Honda. I've seen it on Subaru, where the filters don't meet the OE specs. They don't have the drain back valve. They're a cheaper filter. And the car doesn't have oil pressure for that first 3 seconds, 2-3 seconds to start up as it's filling everything back up. Where with that drain back valve, it keeps everything from draining out of the oil system. Now you're getting that pressure within a second. Oh, Honda Civic. Okay. Yeah, so next time you change oil, you might want to try a different filter.
That drain back valve is in the filter, you said, or is it somewhere?
Yep, in the filter. So there's just something that, I mean, on Hondas for a while, it was such a problem that none of the aftermarket ones had it. We were using Honda filters. And then the aftermarket got them and we switched back to aftermarket filters for the brand we were using. But we do still see that issue where customers will get an over-the-counter filter and it doesn't have it or doesn't work. So
thank you. I thought I was using a good filter, but the Amazon match doesn't show that it matches. So maybe that's why.
Maybe. So what you might want to do just for fun, spend a couple bucks, get a factory Honda filter for it and see if the problem goes away.
Okay, good point. Thank you.
You bet. Sorry, I didn't think of it sooner, but it's kind of Monday except for it's Tuesday. So oil galleries and lines, the main oil gallery runs the length of the block and connected to most other galleries. And so gallery, all that is a passage inside the block that oil is allowed to go down through. I don't know why we use a fancy name for it. It's just an oil passage. And there's passages drilled from the main galley over to feed the main bearings, up to feeding the camshaft, the cylinder head. So we have 2 passages in the block. One is called the galleys, which are the ones that are under pressure. And then we have their oil return, which is just open area that oil is just going to fall through that and come back. So those are normally not machined. They're part of the casting. Crankshaft journals are drilled to carry oil from the main journal to the rod journal. So there's actually hollow passages inside the crankshaft. Some engines use separate oil lines to carry part of the oil flow. So, for example, a Toyota 3.5 liter engine had oil lines on the outside of the cylinder heads, moving oil from the block to the cylinder head. So we've seen that over the years. Mercedes did that on their 6 cylinders. And I know that's, no, I'm sorry, that was BMW did that because I replaced a lot of those oil lines. So we do see that. Some are solid steel lines, some are flexible line, high pressure hose. Some rods are drilled through the full length to carry oil to the wrist pin. So again, it's an engineering choice. Do I want to splash lubricate the wrist pins or pressure lubricate the wrist pins? Well, if I want to pressure lubricate them, now I need to have a hole drilled all the way up the connecting rod, connecting oil pressure from the connecting rod journal all the way up to the wrist pin. So again, how long do I want the engine to last? How much horsepower am I getting out of it? What do I think I need to do? So everything is based on cost and longevity. If it makes it 500,000 miles without it, why would I do it? On the other hand, if it breaks at 50,000 miles without it, and then I put it in and it makes it 500,000 miles, now I need to, do that as part of my build. So it does vary by manufacturers, engine design. Others have tiny holes that line up with the crank journal once every revolution. These are a spit hole that will actually spray oil onto the side of the cylinder wall or up onto the piston for cooling. So here is oil flow through an engine. So I'm picking it up. We're pulling it in to the pump, going out to an oil filter, then to an oil cooler, and then up to my main galleys, down to my crankshaft, up to my camshafts, and then it's going to get to my lifters and my scissor gears, which are my variable valve timing. So here we can see the flow. So the oil pan's coming up the oil strainer, oil pump. Well, if I have too much pressure, we're going to dump it back to the oil pan and the pressure relief. Then we got the oil filter, bypass valve, oil cooler, main oil hole, with my main galley. From here, I'm going to feed the crankshaft, my left and right cylinder heads. Then I have my camshaft journals, my cams, valve lifters, and last but not least, scissor gear. And if you notice, each of these, when we're done using that oil, it goes back to the oil pan. So the more oil I flow at better pressure, the more oil I can send to all these places and get good oil returned back to the pan. And as I return it back to the pan, I'm getting rid of the heat generated in all these places. If I have lower oil pressure or less oil volume, my crankshaft's going to get fed pretty good. But as it comes up here to the cylinder heads, the cams are not going to get as much. The lifters might not get any or very little, so I might get some lifter noise. My camshaft actuator, my scissor gear for my camshafts is the last thing in line. So it's going to get, that's why we get variable cam timing codes and other issues anytime someone's low on oil or has an oil pressure problem, because it's the last thing in line. We protect the stuff at the bottom, it gets oil first, right? Because this is catastrophic failure. These other things are warning signs. That's why you'll hear tapping noise from the lifters or variable cam timing codes when we're low on oil or low on oil pressure, because that's how it feeds. So obviously, if I put in more pressure and more volume, not only am I able to get oil all the way up to the top, but I'm also going to return more oil from each of these places, because remember, none of these are completely sealed. They're all designed to have oil squirt past them and go out. Just the resistance of that is what allows me to have back pressure on the other side. We still have oil flow, just like in the electrical system, we had current flow through a resistor, but we had a difference in voltage between the two sides. Same things here. So the resistance here is the crankshaft, connected rod, pistons, all these camshafts, everything else. These are resistance, and each of these is going to use some of our oil pressure and get rid of some of it back to return. So that's where, going back to that discussion argument you had on the forum, really, it doesn't even really pass the smell test. What, it all goes to the top and sits there? That's not how the system works. A little knowledge can be a dangerous thing.
Yeah, you're telling me.
Well, I know cars, but you certainly wouldn't want to see me try to fly a plane. So, you know, it's all relative. According to the chart on the previous slide, which component is the last to receive oil pressure? Number 4, the valve lifter, right? I mean, scissor gears after that, but I didn't give you that as a choice. So oil pan has oil. It's not part of our pressurized lubrication system, crankshaft and camshaft, and then valve lifter.
Brian, what
Yes.
is the scissor gear again? What does it do?
What's that?
What is the scissor gear again? What does it do?
The scissor gear? The scissor gear is another name for a camshaft actuator.
Okay.
So here's just another diagram of showing oil flow. Again, oil pan, pickup, oil pump, oil filter, main galley, which feeds our crankshaft. These little lines go from our crankshaft to our connecting rods. And then I'm going to feed oil up to my camshafts. And I'm going to have some oil I'm going to spray back onto the timing chain. And that's an oil spray nozzle they're showing there. A lot of times timing chains are only lubricated by the oil that's forced out of the camshaft up top, and then it drains back the front of the engine. So again, back to the discussion, high pressure, high volume, I'm putting more oil on my timing chain because I have more oil returning. And we talk about the bearing receives oil from a hole drilled through the bearing support. Insert has a hole that aligns with the one in the bearing support, and oil passes through it and engages the journal, pulling oil around the journal. And oil is constantly forced through the bearings. So here is what I'm talking about. Here's our oil hole. The bearing's going to set in here and have a hole, which it does. So here's the bearing. Here's the journal. And so this oil is going to be allowed to be spun around the inside here. And since it's under pressure, it's going to be pushed out both sides. So there's no seals on the side here. And here's an oil squirt hole they were talking about. But there's no seals on the side. So this has a very tight tolerance bearing with oil squirted in the middle of it under pressure. So since it's squirted in the middle and it's rotating, it's going to be forced out both sides. And it's going to be spun all the way around. So that oil is constantly coming out both sides. So I have to put enough volume in to create back pressure, because the oiling system has what? Leaks. It's not sealed. We're flowing oil out past all these bearings. So I need to make enough volume to create that pressure, because that pressure is generated by back pressure. So if I have a low volume, I'm going to have low pressure because I'm not generating sufficient back pressure to the size of the leaks I have. That's also why as engines wear, oil pressure will drop. Because if I originally had 1/1000th of an inch clearance between the bearing and the rod journal, and now I have 1.5 clearance or 2,000 clearance, exponentially, that's huge, because it's not a 1-to-1, which means I'm going to what? Lose more oil out the sides, and it takes more oil to fill that gap. So that's why we use higher pressure, higher volume pumps, so that they're going to, again, keep the engine performing properly as it wears. So squirt oils and oil galleries, heavy duty engines have oil nozzle that sprays into the bottom side of the piston. We normally only see that on bigger diesels. I'm not aware of any passenger vehicle that does that. Oil is fed to the cylinder head through oil galleys onto the camshaft bearing and valve train. And oil drains back to the oil sump through oil drain back holes located in the cylinder head, engine block, and the big area where the timing chain is. If there's a timing chain, it's going to come right down through the front. Oil retained in engine, and we retain oil in the engine by using gaskets. sealants, which is kind of a liquid gasket, and seals. And although the terms get really convoluted by manufacturers, as a rule, like we're going to use a gasket, and keep in mind a sealant is a type of gasket between two pieces that don't move. I'm going to use a seal between something that doesn't move and something that does, like a rotating shaft. So I'm not going to use a gasket to seal the crankshaft, but I'd use a gasket to seal the oil pan because the oil pan and the block don't move. So I would seal them together and use a gasket. But since the crankshaft is rotating, I need to have a seal there where one part is not moving, the block, and the other part is the shaft. So oil seals are used at the front and rear of the crankshaft. We use them for the camshaft. Anytime we have a rotating shaft, we're going to use a seal. If it's two things that aren't moving, we're going to use a gasket. And RTV, which stands for room temperature vulcanizing silicone, what we'll use. We also use an anaerobic sealant on some specific applications. If you need to use an anaerobic sealant, the manual will call for that specifically. So we see that on some European engine assembly, some other real limited stuff. And the manual, not only will they tell you they want an anaerobic sealant, they will give you the Loctite part number or the Permatex part number that they want you to use. So, I mean, so don't get intimidated of how do I buy anaerobic sealant? Yes, you can go buy it. They sell it at the parts store. But you're just never going to use it unless you're doing something very, very specific. I think the last tube I bought of it probably 15 years ago, 10, 15 years ago. And I mean, it's still good. It's still in my toolbox, but you use it so little. So that is, you know, and that the anaerobic sealant is normally used when we have two finely machined aluminum surfaces and we're putting them together and we're torquing them and we don't want any space between them. Where a silicone will give us a little bit of a space and the anaerobic will not. The other big difference is the room temperature vulcanizing silicone needs air in order to cure, where an anaerobic sealant will cure in the absence of air. So consequently, silicones, when I put it between two things and I tighten them up really tight, the silicone in the middle doesn't necessarily seal, although they do have some modified silicones now that do a good job of that. But it seals on the outer edges, and that's why we'll get wicking through. Their anaerobic sealant, which is much thinner, when you put it together, it cures hard all the way through. So it's again, just a different material. So here's an oil pan gasket. So in this case, we have an oil pan gasket. This is only, I could also make an oil pan gasket using RTV. And many manufacturers no longer use regular gaskets. They use RTV from the factory. And you can buy a lot of different kinds of RTV. Any kind you buy, you need to make sure that it's oxygen sensor safe. Because and they do sell silicones at the auto parts store, the cheap ones that are not oxygen sensor safe, and they'll actually ruin your oxygen sensors. They'll poison them. So great, you save $2 on that tube of silicone, and you just eliminated 4 oxygen sensors at $100 each. But good job. So you do want to make sure you use. So I tend to, you know, in the shop, we don't even have any of the non-oxygen sensor safe silicone, even though I could use it for a differential or I could use it for, you know, a thermostat housing or coolant stuff that's not going in the engine oil system. But why? So we generally use the oxygen sensor safe silicone and everything. A lot of times we use the ultra gray or the ultra black or the two common ones that we see used in the shop because they duplicate the OE colors. There's a European company, Durco, that we use on a lot of the European stuff. If I'm doing differentials or doing stuff underneath the car or really gear oil type stuff, then we usually use the right stuff. I mean, so some covers stuff we use, it's actually called the right stuff, and it's an O2 sensor safe silicone, but it sticks to everything. So it's much harder to clean off than an ultra black or an ultra copper or any of those. So ultra coppers are high heat, very, very limited use that we use that for. There's only 1 or 2 things I use that for. But they clean off reasonably well. The right stuff, you're going to work cleaning it off if you're ever the one to take it back apart. I mean, it seals up good enough. I've bent differential covers trying to get the cover off because it sticks that good. You got a primer and you're bending the diff cover and it won't come off. It's like, so the stuff works great when you put it on. You just don't want to be the guy that has to pull it off, clean it, and reuse it. But that being said, there's certain applications that it's the stuff. It's what you want to use. And here we see our front and rear oil seals. Some manufacturers will use a slinger. And what the slinger does is it directs a lot of the oil away from the seal. So the seal will last longer. It's not trying to hold back as much oil. One manufacturer, MG, back in the up into the 70s or even early 80s, didn't even use a rear main seal. All they used was a slinger to bring the oil back. And that's why those cars always dripped, because there was no rear seal. Oil pressure indicators. So we do care about what oil pressure and level is. So I can have an instrument panel mounted gauge or light. The light's going to be a switch. The gauge is going to be a sensor, right? Because the gauge has to use variable resistance, where the switch is an open close switch, lights on or lights off. Electric oil pressure gauge uses a different sensor unit than used by electric water temperature gauge, obviously, but the same principle applies to the electrical circuit. So, for a cooling system, we're going to use basically a thermistor to change resistance with temperature. Here we're using something more like a map sensor that changes return voltage or change resistance with pressure. Some vehicles use a warning light to indicate when pressure drops below a certain point. To put that in perspective, most systems require 13 to 30 psi oil pressure, somewhere in their spec. The oil pressure light usually comes on around 0.5 to 1 psi. So by the time the light comes on, you have a problem. Use the term warning light very loosely. Some cars have a gauge and a light, which is a good idea. Or some other warning light, like check oil pressure. So this vehicle has a gauge, but it has a light that comes on that says, hey, dummy, look at your gauge. That's helpful. The other helpful thing about this is now I can have you look at the gauge at 20 psi or 10 psi or whatever we program it to. Here's our regular oil light. And here's a gauge. If you're reading 0 on the oil gauge, my first question is always, what do the other gauges read? If they all read 0, I'm guessing it's an instrument cluster problem or a fuse problem and not an oil pressure problem. Following the logic there? So here are our two circuits. Here's our oil pressure switch. We have our light. Our light is powered. The switch has one wire to it and it controls the ground. So depending on the position of the switch contacts, we're either going to make contact or not make contact based on the oil pressure going in the switch. So we have oil coming out. It's going to push it. And when it does, it takes the light from being on, it releases the contact, and now we're no longer making contact and the light's off. Simple series circuit, right? Well, we have a switch, power supply, and a load. Simple series circuit. So if I have a problem with this or I want to test it, what I'm going to do, I'm going to disconnect this wire and touch it to ground. Does it come on? Disconnect it from ground, does it go off? That just proves the rest of the circuit works. Time to think about putting a pressure sending unit. Now, one thing we always do in industry is that if I have, because we have cars all the time come in, the oil light's on. Well, how long has it been on? Oh, like 2 weeks. Okay, so I'm guessing it's not a catastrophic failure. But, how's the engine sound? And sometimes people say, well, the engine sounds really loud, or other times they say it sounds fine. Regardless, one thing we always do when we replace the SIN unit is we need to know what the oil pressure is. So in industry, we're going to pull the send unit out. We're going to put a mechanical oil pressure gauge in it and test oil pressure. And then when it tests good, then we'll put the send unit in. If it tests bad, then we let the customer know. Because the liability is so high for a shop just to throw a send unit in it and let me know what happens. When you're talking the cost of an engine, you're going to run oil pressure test and verify oil pressure is good before you send it out the door. Even though you think it probably is, occasionally you get surprised. I've had cars that, man, I'm sure it's just a bad send unit. This car sounds great. They've been driving it. You check, oil pressure is well below specifications. So minimum pressure warm might be 20 PSI and we're sitting at 8 or 6. It's like, whoa, we got a problem here.
Generally, the sending unit can be replaced without flushing the oil out.
Oh, yeah. Oh, yeah. Oh, absolutely. It only has oil pressure there when the engine's running. So the engine's off. And when you unscrew that, you're going to get just a little bit of oil dribble out of it. And you just screw it back in. You do not want to use a lot of Teflon tape or anything else on the threads, because remember, you're completing your circuit to ground through those threads. So those threads are going to be pipe threads. They're going to be tapered. So you don't want to crank it down and tighten it until you can't tighten it anymore. Because if I'm putting a steel wedge and I'm screwing it into an aluminum housing, who do you think is going to give first? The aluminum housing. And that actually happened on one of the school cars, not my class. Another class, they're doing oil pressure testing. They're screwing the thing in, popped the $150 oil pump housing.
That's also interesting. When you say school cars, and you mentioned that throughout the course, what are those cars?
Those cars are on the campus that they don't let me go to anymore.
So the school owns the cars and they are used to as a lab material.
Okay. Yeah, so we own about 20 cars that we use for lab. And so like when I was on campus, I had about 6 or 7 cars that were only for my class. And I was kind of a jerk about it because I'm the one that got them all running. And other teachers would use them and they wouldn't be running when my students had a lab. So I just went and said, these are my cars. These are the ones that have the things in them that I need for doing these different labs. And you guys don't get to use them anymore. Like one of them's a little Honda, 4-cylinder Honda, like a 99 or 2000 Honda. And I use it for teaching valve adjustment because it and the Honda Odyssey are the only 2 cars I have there that have a mechanical valve adjustment. Well, last time before I got it running, because it wasn't running, I used it. I went to use it again. The car was torn apart in pieces. They broke the bolts going off that hold the camshaft. I don't know what they were doing on it. Like they were going to practice a timing belt or taking a camshaft off or something in another class. Instructor did nothing. No one did. So I was there after school, drilling out broken stuff, putting thread inserts in. They lost a lot of the parts for the valve train. I got a junkyard to donate all the extra missing bolts and valve train parts. Got it all put together. When I got it put together, I went to my boss. I said, no one else uses this car. This thing was a boat anchor. No one else wants to fix it. I took my free time to fix it. My students need it. It's the only car we have here that we can do these tasks on. So that key stays locked up in my office. I'm the only one that has a key for it. So, you know, I did that because, and again, it's not trying to deny other students things, but, you know, if people aren't going to put things back so the next person can use it. I mean, when I got to school, when I started working for the college over 3 years ago, they didn't have 5 cars that started and ran that I could do a lab with. They had way more than 5 cars. They had about 15 or 20 cars, but there wasn't 5 that I could go out, start up and do a lab with. They didn't have 5 cars that ran. It was take apart and park, take apart and park. So I spent the next year plus getting the cars running or getting rid of them. And I got it to where I had everything running. And that's why I get really irritated when, what do you mean it's apart? What do you mean pieces are missing? Because no one wants to push a car up. And I think it's a different experience when I say, yeah, do a compression test on a car that doesn't start or run and we know it's broken, or, you know, do this test, but it doesn't look like a real car because half the pieces are missing on it. Or, I mean, it's just not, I just don't think it's the same experience. And how do I teach people to put things back together and take care of things if everything they're working on is junk?
That is so true. Can I ask you another question? You mentioned something about if the light or the pressure gauge is low, you ask the customer, what about the other gauges, right?
Right.
So you mentioned it could be the instrument cluster. So I'm not connecting those dots, with our
Okay.
electrical and everything. Where is all that?
Okay. So if my oil pressure gauge, I set it back on this picture here, right? So my oil pressure gauge in this case reads 0. What does my temperature gauge read? What does my gas gauge read? If everything reads 0 or low, that sounds to me more like I have a power problem going to the cluster or back cluster, because odds are we didn't run out of gas on a cold engine with no oil pressure, right? So if everything is reading low or everything is reading high, I think it's a reasonable question to go, is the problem really the one system I'm concentrating on, or is it something that all of these systems share, which might be a gauge fuse, like in the case of GM, which is what we're looking at there, or a bad instrument cluster or something. I mean, we need to at least ask that question. That's why, even though the customer might be complaining about one thing, I've had this a lot of times they don't put the correlation. Well, the gas gauge doesn't work and this doesn't work, but all they're focused in on is they don't have oil pressure. Because I don't get necessarily a warning light for the engine being cold. I may get a warning light that I'm almost out of gas, and the customer just writes it off as, well, my gas gauge doesn't work right. And a lot of people have had that. So sometimes people don't always put the dots together. And that's why, if all the other gauges are working normal and the oil pressure gauge is reading 0, I have an oil pressure gauge problem. Whether that's a SIN unit, a gauge, a wiring, whatever, I don't know till I test it. But if all my gauges are reading 0, it's probably not an oil pressure gauge problem. It's probably a problem that affects all the gauges. Does that help?
Yes, it does. So that's that part which you look at directly behind the steering wheel, and it's an assembly, right?
Right.
Okay.
Yeah. So if the whole assembly's not working, I'm thinking it's not an oil pressure problem,
Of course, of course.
But and we say, of course, but people a lot of times don't look past either what the customer complained about, or don't look past that one thing. Just like when we were talking about charging systems, and I've had people that have put 4 alternators in, and I ask them, well, does the charging light work? I don't know. I didn't check. Well, we know if the charging light doesn't work, most of the time the alternator doesn't work. Why wouldn't we have checked that at least 3 alternators ago? But people don't, because they get so fixated on what's not working. They don't take a breath, stand back, and look at the whole thing.
Yes, thank you so much for that explanation.
You bet. So cooling the oil. So we're going to get into our next chapter. We do 2 things. We lubricate and we cool with oil. So there's a couple of different ways we cool the engine. We define it into liquid cooling or air cooling, as we'll see shortly. Both systems use oil also to cool. So the oil, you think about it, heat's generated by friction. I need to move that heat that's generated and dissipate it. So I'm going to dissipate some of that through my oil pan. I'm going to dissipate some of it in the other metal of the engine as I circulate it, drain it back down where it's not under pressure. So that's what's, my timing cover is made of aluminum. My blocks cast iron of aluminum. I've got a lot of area that I'm going to heat and, going to dissipate. And sometimes that may not be enough. So it so it may not move in. So some oil pans have fins. And so what we've done is we've added oil coolers. There's 2 different kinds of oil coolers we see. One is mounted directly underneath the oil filter. Very, very common today and very popular today. One of the reasons is that I can manufacture this engine assembly and drop it in the car. I don't need to hook up external things, because the oil being right below the oil filter the oil's flowing through it. We just put a couple little hoses that connect right back to the cooling system of the engine, right on the engine. So when we put that engine assembly in, it's complete. So this is a European way of doing it. We first started really seeing this in the 90s. This is by far the most popular way to do an oil cooler today. Nissan does it, Europeans do it, a lot of manufacturers do it this way. The old school way of doing an oil cooler was we would put a cooler, kind of look like an AC condenser, in front of the radiator and have hoses that went from the oil system under pressure all the way up to the front of the engine, through that cooler and back. And GM did this for years on their trucks, where they actually had an oil cooler built into the radiator along with the transmission cooler. Some of them have external oil coolers. So again, this requires being tied in where I have a port where I can pull oil pressure off and feed it back in. So a lot of these systems have a spacer plate that goes between the oil filter and the engine block, and it has a pressure and a return. And so we're just going through the filter, then pushing it out here, bring it back here, then it goes to the rest of the engine. So you can see if you have a problem with the oil cooler, like a leak, you're not getting oil to the engine because it's between the oil filter and the main galleys that feed the crankshaft and everything else. So that's why an oil cooler hose failure or something like that, or oil cooler hose failure leak, is a major issue, and why shops really recommend you take care of it right away, because if it lets go completely, you're going to lose an engine before you even know you have a problem. So those are the two systems we use. Now, this first system I showed you, because we have coolant here and because we have oil here, one of the signs of a blown head gasket, where we're getting coolant into the oil through the head gasket, has long been that the oil turns kind of a chocolate milkshake color. You get a lot of water in there, it becomes a vanilla milkshake. This will cause that same symptom. So many people have misdiagnosed a bad head gasket on a vehicle, and it's actually the engine oil cooler. And so a couple of different ways you can go about it. You can take the hoses off, bypass it, and see and run it, see if you get any oil dripping out of the coolant side. So there's a lot of different ways you can go about it, testing it, or you can just change oil, clean it, bypass it, see if the problem goes away or if it comes back. You can pull it off, pressure test it on a bench. Several different ways you can go about trying to find out whether that's it. I've seen a lot of oil coolers go bad. Very, very common. Much more common than blown head gaskets are today. So I wanted to let you know about that. Like I said, not all cars have these. Not all cars have oil coolers, but this is something that is still often misdiagnosed. And since we're getting into cooling systems next, I wanted to touch base on that.
So if
So
you
we
had
did
that kind of,
what's that?
I'm sorry. So if you had that situation where the two fluids mixed for either head gasket or the oil cooler problem,
Right.
how much cleanup is it necessary? You know, you're the repair person and you want to isolate that. So how much effort will you invest into cleaning that area where they mixed?
Right. So you need to have it clear so you can see if the problem comes back. So I know, for example, Mercedes years ago had a problem with their head gaskets leaking, and I was doing it a couple of weeks, and they put so much oil into the cooling system that the hoses were the upper radiator hose lower were actually sweating oil out of the hoses. So we actually had to put all new hoses on them, and we actually ran the engines, and we go through about a half gallon of simple green, putting simple green in the engine with water, run it, dump it out, more simple green, more water, run it, dump it out. And that's probably the worst contamination I've ever seen. And that was in the cooling system because it was an oil pressure port that was pushing oil in the cooling system. So if you have oil in the cooling system, it's a very different than if it's coolant in the oil system. Coolant in the oil system, you'll see that really white milk chocolate when you pull the dipstick. So I'm going to do whatever I need to do, bypass the oil filter, bypass the hoses, loop them back to themselves, whatever, to seal the cooling system. And then I'm going to change the oil, and I'm going to let the oil drip for probably a half hour before I put the drain plug back in, and then put fresh oil in it. And that's normally enough in the oil system to where your oil is going to look normal now. And then I can tell if drive it 100 miles, 1,000 miles, and see if the problem comes back.
Thank
So
you.
very, very different amount of effort whether I'm trying to clean the oil side or the coolant side.
Oh, cooling side is a much more
Coolant side
involved.
is much more time consuming, much more involved. Now, fortunately, with the oil coolers, what normally happens, because my cooling system operates at a pressure of around 15 psi. My oil pressure, although it operates at a much higher pressure, 50 psi, 60 psi, it can force oil into the cooling system. So you may get a little bit of that. Where we really see it happen is when the car shuts off and that coolant that's under pressure at 15 psi, and now there's 0 psi in the oil system, and it pushes that coolant into the oil system over the next hour or two while it's getting rid of its pressure as it cools down. And that's why we see more coolant in the oil than oil in the coolant on the oil coolers, where you think it would be, hey, it's under oil pressure, it'd be going the other way, but it doesn't seem to be.
Thank you.
Things don't always make as much sense as you'd like them to, but that's what we see. So let me get into here. Just 1 minute here. Okay, I just turned on the PowerPoint review quiz for chapter 14. And which is our engine lubrication. And let me turn on engine cooling so Cynthia can see the PowerPoints. Or I
Thank
will
you,
hear
sir.
about it as soon as I start talking about it. And I'll get
All
the
right,
other
sir.
stuff. I'll get the other stuff turned on for it shortly.
I'm the PowerPoint police.
Yeah, I got the PowerPoint's the only thing I turned on right now, because I got to go in and turn on the chapter and a couple other things that I have a couple labs in it also that I'll turn on. I'll get those turned on after class. But I knew if I went to a new PowerPoint and it wasn't turned on in Canvas, somebody would be reminding me, and I thought I'd get ahead of it this time.
Yeah, the PowerPoint police, sir.
Yep, all done. Got it turned on. I see the little emoji there. What are you trying to tell me?
It is funny, right?
Yep. Oh, absolutely. Okay, there's that. And share screen.
So that last thing that we're talking about, that auxiliary oil cooler that's kind of built into the block, I guess.
Yeah, it's added on. It's like a little spacer that goes between the oil filter and the engine block.
Okay.
They're about 2 inches.
How
thick,
common were you
roughly.
saying those are? They're mostly in high performance, or they're more common in everyday engines, or?
Everyday engines, we see
Yeah.
them on a lot of European and Asian engines, not so much on domestic, but a few.
Okay.
And then, of course, the old school where you put a transmission cooler, radiator, and oil cooler, everything else up in front is, of course, popular. And let me go grab a little more to drink.
Good morning, everybody.
morning.
Looks like not too many people attending today.
Down a little bit, got 21, 20. A lot of times having a day off, people get out of sync. I did see some people try to go to class yesterday. I did send an announcement out. Okay, so I should be sharing my screen. Yep. Okay, so cooling system theory. So in here, we're going to talk about air-cooled and liquid-cooled cooling systems, the components of the cooling systems, and the reason why we don't have air-cooled cooling systems anymore, and that's because of emissions. So the whole idea of the cooling system is to take that heat energy and get it out of the engine. We're also going to discover we have more than one kind of cooling system. So cooling system effects on lubrication system, engine emissions, and fuel economy. The cooling system failure, engine overheating. That's the one that people normally think of when they have a cooling system failure. The failure that's very, very common, but customers normally don't complain about directly, is not allowing the engine to reach its ideal operating temperature. So this can be a symptom for the customer, might be that my heater doesn't seem to work good. So I'm going down the road, I start up my car and I've been driving for 15 minutes, but yet inside of my car is still kind of cold. It doesn't feel like my heater works very good. So this can be an engine not allowing to reach operating temperature. The other thing that we see a lot is that the car failed smog because the self-diagnostic monitors have not completed. Well, they haven't completed because the car didn't get to operating temperature to allow them to complete. So a lot of times where we diagnose the, we call it an overcooling issue, is from a smog failure more than anything else. Now, obviously engine overheating, that's the car came towed in on the tow truck. You know, that's what we normally think of as a cooling system malfunction. Modern passenger vehicles can have several cooling system types designed to control operating temperature of mechanical and electrical assemblies. So I can have a cooling system for the internal combustion engine, which is what we think of as cooling. And certainly if I have an ICE engine, I'm going to have that on anything built since 1991 and sold in the US. Supercharger can have its own cooling system. Turbocharger could. High voltage battery, hybrid motor generator assembly could have a cooling system. And these may be shared with other things, or they may be completely independent. So we do have all these. For example, the Tesla has, we call it a cooling system, but it's really a climate control system because it's able to both cool the batteries and heat the batteries. So we're now seeing with it, when it comes to battery technology, it's not just about cooling the batteries, which is where we started. We put a fan and pull air past to cool batteries off. It's now really about temperature management. And the same thing is true for my internal combustion engine, my supercharger, my motor drive. Things don't work well when they're too cold, and we don't want them to get too hot. So since they don't work well when they're too cold, they're going to consume, they're not going to be efficient users of energy. And if they're not efficient, that means emissions go up. So we want to get warm extremely quickly, or get to normal operating temperature extremely quickly, and then stay there. So we want to be very, very stable. So without properly operating cooling systems, engines self-destruct in minutes. An engine will not last very long without a functioning cooling system. And minutes is not an exaggeration. I can't tell you how many customers I've had that the overheat light came on going down the road. Well, I just wanted to get to the next exit because I didn't want to stop there. Oh, it was only 2 miles. It was only $3,000. So we went from a water pump repair to a major engine repair, or a radiator repair to a major engine repair. You know, people ask me all the time, whether it's an oil light being on or a car overheating, is it safe to drive? And my answer is always, it's cheaper to tow it. Well, you don't know what's wrong. Right. I don't know what's wrong. That's why it's cheaper to tow it. Because really, you tow it, you're out of tow. And gee, you could have driven it, so you're out the money for a tow. On the other hand, you try to drive it and you shouldn't have, and now it costs you a major engine repair. I think it's cheaper to tow it. So I always recommend, someone calls on that, I always recommend tow it. But I don't know what's wrong, right? And I don't either. The light came on. I do know if the longer the light's on, the more damage that can happen. Let's get it towed in. And different cooling systems will operate at different temperatures. So here's an example. Engine cooling system for the ICE engine, for the internal combustion engine, normally operates between about 180 and 220. It's a good rule of thumb. We do have some systems that operate a little warmer than this. A supercharging cooling system on the same engine operates between 100 and 140. That's a very different temperature range. So what's normal for one component or one device or even one engine may be slightly different on another. And I already talked briefly about my high voltage battery cooling system. Air or liquid removes battery cell heat when under prolonged high amperage draw. High voltage motor generator cooling system, a liquid coolant, prevents the motor generator overheating in full electric and hybrid gas vehicles. High voltage engine control module cooling system forces air or liquid through or over aluminum heat sink surrounding the high power transistors for each link of the three-phase circuits. So, occasionally I have people that are really into computers. If I have a serious gaming computer, it'll have a liquid cooled heat sink to keep the processor cool. So we do liquid cooling of processors on home computer units, commercial computer units. It would make sense that we would do that on some automotive computer units once we get to that certain temperature threshold. On modern vehicles, there could be separate cooling systems for different components. Is that true or false?
True.
True, absolutely.
True. Electrical cooling, one question I have. Like a transformer and winding, they had some special liquid oil for cooling in the transformer, but in the battery, what is the difference of the cooling system?
Well, it depends on the cooling system. There's several different styles, but what they're doing is they are either going to move air over the batteries or they're going to move liquid around the batteries to dissipate heat, or in the case of Tesla and some other manufacturers, heat the batteries up. So I can use a dedicated liquid system. Mercedes does this. And then that liquid system could be tied into an air conditioning system, or like on the Ford Escapes, they actually use the AC system to cool the high voltage battery. And if the AC system didn't work on the hybrid Escapes, then you get a warning light on for the high voltage system, and it would disable the high voltage system because they don't want to damage the batteries. So AC is no longer an option, right? It's required because you're using it to control battery temperature. So manufacturers do it several different ways, but they're not running it through the battery. They're running it around the battery. So I think that might be where the confusion is. So we're putting the batteries and we're going to surround the battery with a liquid, or we're going to surround it with an air that allows us to take the heat that's generated from that battery and dissipate it away from the battery.
Okay.
So heat transfer moves areas of higher temperature to areas of lower temperature. So heat always moves from hot to cold. So you have cold air in your car because we took the heat out of the air, not because we made the air cold. So it's kind of a different way of thinking about it, kind of like our pressure vacuum discussion earlier. But when it comes to thermodynamics, we're always moving heat because heat is energy. The more heat, the more energy. And I can't just get rid of energy, but I can move energy. I can make energy do other things. So for example, I could take electric power, which is energy, and convert it to rotational force. There's my starter, right? So I didn't just, the energy didn't suddenly go away when it went to the starter. It was converted to a mechanical function of rotation. So because of how heat works, it goes from hot to cold. If I want to make something cold, I need to take out the heat. So if you go to your refrigerator or freezer when it's running and you feel the sides of it, they'll be warm because you're taking the heat out from inside the refrigerator and you're getting rid of it on the outside of the refrigerator through the condenser coil. And that's how air conditioning works. How air conditioning works on your house, how air conditioning works on your car, is that thermal transfer. Well, in the case of the engine, what I want to do is I want to just take this heat that I've generated inside this engine and just make it go somewhere else because I can't let my engine get too hot. So we are willing to waste a lot of that heat. So conduction is the movement of heat energy through solids. Convection is the heat movement through liquids or gases, and radiation is the movement of heat through space. So, right, you have radiant heat, you have convection heat, and you have conduction heat. So heat is produced during the combustion, is not used productively. This is where you get the fact that automobile internal combustion engines are very low efficiency, even with all the advances we've done. And that's because what are we really generating when we burn the air fuel mixture? We're generating heat. We're using some of that to push a piston down, but we're not using all of that energy. And this diagram really demonstrates that. So, 5% of internal friction and related heat and energy components. So as I reduce internal friction, I'm going to have less loss there. My pressurized cooling system, which is designed to prevent evaporation, is going to take a third of the energy. So the third of the heat energy that my engine produces, I'm going to put into my cooling system and I'm just going to give away to the air. Oh, and if it's a cold day, I'll let you have some of it through your heater. 25 to 30% is used to power the vehicle, and another third is going out the tailpipe in heat energy. So this is one of the criticisms, and I think it's a valid one, of our internal combustion engine, is that we generate a lot of energy because heat equals energy, and yet we're really not utilizing it. We're really not using it effectively. And so I think there's a lot of possibilities, and people are playing with different things as far as getting the energy out of the exhaust or getting the energy out of the cooling system and managing that to get more efficiency out of this. So we have the combustion efficiency that we talked about, which is about 90%. But even that, I'm only getting about 25 to 30% of the energy I produce to actually make the car go. So this is why you see a big push for electric power and some other things, is because an electric powered vehicle, I do generate some heat through a motor that I lose, but it's very small compared to the amount of energy I'm able to put rotationally to make the car go down the road. Anything about, we have made a lot of advances in other technologies when it comes to wasting heat from exhaust. I don't know how many of you have a tankless water heater, but if you do, it probably has a plastic vent pipe going out through the roof, because the tankless water heater uses it's very, very efficient. We're putting all that energy into the water. If you have a high efficiency furnace at your house and you've had that replaced, or what they call it a condensing furnace, but usually high efficiency, 96, 97%, the vent pipe for the furnace is plastic, because we're burning, natural gas or propane, but yet we're getting all the energy out of it. So therefore the exhaust is cold because we've captured that energy. That's where that efficiency has gone up. So we've seen this technology in appliances. We're not seeing it in automobiles. And, I have to wonder, is it not practical in automobiles? Kind of have a hard time with that. Because there is some practical applications we could do with it. Or is it just that we don't have an interest there because we're already being told we're going in a different direction? I don't know. Fair question. In other words, do we hate the technology so much we don't want to make it better? Or, where's the stuff? Because certainly you look at, especially on a hybrid vehicle, I could turn that heat energy into electricity from the exhaust. And there's the technology out there to do that. Well, if I'm getting a third of my energy from rotating the crankshaft, and I could pick up another third and generate electricity out of it efficiently, which means if I could generate electricity from exhaust heat, I could probably generate electricity from what? Coolant heat. So if I can convert heat to electricity, and there is technology out there that does that, not currently cost effective for automobiles, but the technology is there. Now what? What if I could get 96, 97% efficiency out of my internal combustion engine? Would that change our opinion on it? Right? Because then theoretically, I'd use what, a third of the fuel I'm using now? Just food for thought. Like I said, I love technology. So there are two types of engine cooling systems, air-cooled and water-cooled. Now keep in mind, both of these use oil. Oil is always going to help us cool the engine. We don't define it as an oil-cooled engine or a liquid-cooled. And I put water-cooled here. That's generic. I should probably just change that to liquid-cooled. Would probably be a better definition. Because we don't run water in our cooling system. We run liquid. So it's a liquid-cooled system. So the cooling system configurations, there's two primary configurations that we use. One is a standard flow and the other is a reverse flow, as we'll see, for our liquid cooling system. But my electric cooling system has to have a pump. And what we're going to do is we're going to pump coolant from the engine. And here's my cylinders. So I have coolant surrounding my cylinders and my water jackets. And I'm going to pull coolant out as it gets hot on a standard flow into the radiator. As the radiator has air go through it, that heat energy is going to be given to the air. And then the colder coolant is going to be brought back into the engine around the water jackets. The hot stuff comes out the top and so on. Also, if you notice our heater core is the device that's in the dash that allows us to have warm air inside the passenger compartment. And it also has a loop. And the loop here goes through the heater core and back. So we're constantly flowing coolant through the heater core. Some older systems had a heater control valve where you had a manual valve that you could open and close the heater to allow coolant through it or not. And we saw those used really up until the 80s. Through the 80s, we used that. Pretty well went away in the 90s. I think some early 90s still used them. And so a customer might complain that their air conditioning doesn't work well and thinks they need an AC service. In reality, it may be that the valve that closed off coolant flow of the heater isn't closed. So you're putting 220-degree air into there. No wonder why the AC is not getting cold. Newer systems, we use what's called a blend door. So we circulate coolant through the heater core all the time. And we just use a door to change the mix between hot and cold air. So we no longer need to turn off the coolant flow to the heater core because the heater core is now actually part of our cooling system. Yeah, Tim.
That's exactly, I think, what I was going to ask. I was wondering if the engineers, if you think, take that cooling effect of the coolant going through the heater core into account for how they design the overall heating system.
On modern,
question ties into in mine. I have it bypassed. Actually, I don't even have the heater in the Bronco because I don't like the heat that it generates in the cabin because I don't need it around here, right? I don't need it. So I have it bypassed, but I've always wondered if that extra coolant flow through that is supposed to help the overall system.
Okay, so yes and no. Okay, so the short answer is yes. On a modern vehicle without a heater control valve, you should never bypass the heater core because that's part of the design system. We actually see emissions go up. We see systems not work right, all those things. On an older vehicle like your Bronco, it would have had a heater control valve. That means it was designed to have coolant flow cut off to the heater core, and the system still operate properly without that additional cooling. So on your Bronco, there's no, you're not going to hurt anything doing it. Now, if you had the heater core there, and you notice if you've ever driven it at slow speed, it puts a lot of heat into the cabin because it's getting rid of a lot of engine heat. So you are putting more of a load on the radiator, which is easy enough. Put a better radiator in it, done. And so, no, I wouldn't worry about that at all on your Bronco. Your Explorer, on the other hand, you'd never want to do that on, right?
Nor
Because
would I,
that
but yeah,
system is
yeah.
designed with a blend door system. So this is where technology has changed, and people go to this old school, well, it's leaking, I can just bypass it. Well, in the days of heater control valves, we could. No harm, no foul. On newer cars, that's a big part of the system. The other thing is that you've probably heard people say, if your car's overheating, turn the heater on. And the reason for that is this is a mini radiator. So if my engine is running warm and I turn the heater on, now I'm blowing air through this heater core, I'm getting rid of engine heat. That's why that works. Because it's basically just a little mini radiator.
Perfect. Cool. Thank you.
You bet. So liquid cooled uses coolant with special antifreeze and anti-corrosion chemicals mixed with water to transfer heat throughout the cooling system. A water pump causes coolant to circulate through the water jackets, block and cylinder head, and air moves through the radiator, and heat energy is transferred from the coolant to the outside air. And so in this cutaway, we see the water pump. You got some arrows here. This is a thermostat, which we're going to talk about later. And then you have a bypass hose. And then this right here is the heater core. So if you notice, the heater core is on the back side of the thermostat. So the heater core gets flow all the time. And so when I'm servicing a cooling system, one of the things it tells me if I filled the cooling system up all the way is if the heater gets hot. If the heater doesn't get hot, then I probably have a big air pocket in the cooling system. So even if my temperature gauge is getting hot, if my heater's not hot, I've got a problem. That means I probably have a big air pocket in there. And we'll talk about how to get that out tomorrow probably. So my thermostat is set for temperature. And once it hits that temperature, it's going to drop down and allow coolant to come through the upper hose and out to the radiator. Below that temperature, it stays closed and forces coolant back through the bypass hose, back to the water pump, back around the block, and so on. So the thermostat is what controls the operating temperature of the engine. If the thermostat is removed, the car is going to run at too cold of a temperature. If it sticks closed, obviously my car would overheat because I'd never get to the radiator. Manufacturers are very specific on their thermostat rating, and we should always use what the manufacturer recommends on a computer controlled vehicle, because all the computer system is designed to have that engine work given the parameters of that thermostat opening and closing at the temperatures that the engineers designed it for. And we'll get more into that later, and more into thermostat as we drill down into this. But you never want to take a thermostat out. That's not a fix. Because as I'm running coolant through the radiator, the thermostat, if you've ever looked at one, the hole's about this big for the thermostat, but the thermostat itself is this big around, right? It's not the whole surface. There's a restriction there. And that restriction is designed because I don't want my coolant going through the radiator too fast. So an example would be if something's hot. If something's hot and I touch it, I'm going to burn myself. If something's just hot and I do this, I go, man, that's really hot. Same thing too. So my coolant needs to spend enough time. I guess I shouldn't have grabbed something green. My coolant needs to spend enough time in the radiator to give away its heat. So if I take the thermostat out, I can actually cause overheating because now the coolant's going through the radiator so fast, it won't get rid of its heat. So how's that for a little food for thought? On that note, actually one more thing. So air cooled always comes up. So this is air cooled right here. So this is a cylinder. If you notice, there's no block here. This is a cylinder. It has bolts that hold it to the block at the bottom and the head at the top. So this is all modular pieces, not one big cast thing. And the air goes through these fins, and that air going through the fins is what gets rid of the heat. So on cold days, it would run very cold. On hot days, it would run very hot. So these engines, as a rule, do not last as long. They're very, very dirty on emissions. And they were used primarily by Volkswagen and Porsche. I need to go back really to the 60s to maybe early 70s, but certainly the 60s to see some of the air-cooled Saabs, air-cooled Subarus, other air-cooled vehicles we had in this country. So Volkswagen went away from air-cooled vehicles by 1984, Porsche by 1991, and like a Volkswagen Bug, they went away in the 70s. The convertible last year was a 79 for a Volkswagen Bug convertible. And they went with the Rabbit. They went with the Scirocco. They went with all these new cars, front-wheel drive, liquid cooled. And they did that because of emissions. But yet we sold air-cooled Volkswagen Bugs in Mexico City up until a couple of years ago. So they weren't healthy enough to have here. They're extremely dirty, cheap to manufacture, reasonably good on gasoline mileage. And so they sold them in other countries without those strict emission standards for the next 30 years, 40 years. Aren't we all breathing the same air kind of worldwide here somewhat? So again, it's always interesting how, goes through. So we're going to talk a little bit more about the emissions on air-cooled engines tomorrow and how that's effective. But I kind of wanted to give you guys that thought because Mexico City has some of the worst smog in the world. And yet we sold cars there that weren't clean enough to be sold here for a long time. Now, to be fair, they were made in Mexico. They were not made in the US. But still, huge pollution. So on that note, everybody, hopefully you learned some stuff today, had a great Tuesday, and I will kick on the other assignments on the cooling system module and do that review quiz. And I will see everyone tomorrow.